When working with integration by parts, the idea here is to take an integral that you cannot evaluate and rewrite it in a form potentially with an integral you can. So if the original statement is of this form where u and v are both functions of x, through the appropriate substitution, I can always get something in this form, with the idea being I may be able to integrate this one when I couldn't do this one. So we want to do a few challenging examples of this concept. The first one, let's consider the antiderivative of the natural log of x dx. Now, right off the bat, you look at that and you say, wait a minute, this doesn't really fit into here because I don't have two functions. Well, actually, I do have two functions. It's just that the second function is a 1. So think of this as log x times 1 dx. Now, the simple rule of thumb with integration by parts is you have two functions. If both of them can be integrated, then either one of them can be the u and the dv. But if only one of them can be integrated, then that one has to be the dv and the other one has to be the u. We don't know the antiderivative of the log, otherwise we'd already have the answer. So this has to be the u. Therefore, the dv must be 1 dx. Now with that, the derivative here, the du will be 1 over x dx, and the v will be the antiderivative, or just x. Now remember, we hold off adding the arbitrary constant until we're all finished with the integrations. Now, with this particular substitution, my answer is uv minus the integral of v du, which is very, very nice because 1 over x times x is just 1. So I'm integrating 1 dx, and that will give us x log x minus x plus c, or if you choose to factor, you could write it as x log x minus 1 plus c. So this one turns out to be relatively simple, okay? So in general, again, the rule of thumb is if you can integrate both functions, it doesn't matter. It's going to be the same amount of work regardless of choice, but if you can only integrate one of them, then that's the one you have to use. Now let's do a similar example to this, but this time, let's throw in a monomial to a power. So this time let's make it x to the n log x dx. Now it's a fairly obvious substitution. Again, I don't know the antiderivative of the log function, so that will be my u, and the x to the n will be my dv. So I will say, let u be the natural log of x, dv is x to the n, then my du will be 1 over x dx, and my v, which would be the antiderivative of this, would be 1 over n plus 1, x to the n plus 1. Now, again, uv okay, minus the integral of v du. Now, minus the integral of v du, but once again, I have 1 over x, and I have x to the n plus 1, so one of those exponents would cancel. So this would be 1 over n plus 1 x to the n dx, which again is a very simple antiderivative. And I'll get 1 over n plus 1 x to the n plus 1 log x. Again, I get a denominator of n plus 1, so that will be squared x to the n plus 1 plus c. Now, this is a perfectly acceptable final answer, but notice I have fractional coefficients and I have an x to the n plus 1 in each term. So once again, it may be convenient to factor this. Now, when you're factoring out the coefficient, right, think GCF, so I would actually factor that term out. So 1 over n plus 1 quantity squared, and I'll factor out the x to the n plus 1, and that will leave me with an extra power, or an extra factor of n plus 1 times the log term, and I just factored this entire quantity out, so that would be minus 1. Both of these would be considered acceptable final answers. The last one, though, probably a little easier to work with because it's not only in a factored form, I only have one fraction. Now let's do something perhaps even more complicated. But before we do, I want to review a little bit of algebra that you may or may not be familiar with, because it's a little bit obscure. And that is when manipulating certain quotients, there are certain things you can do to make your life easier. Now, we already know that anything of the form a plus b, or excuse me, a over b plus c over b is a plus c over b. And we can always add or we can always pull apart. But that also means that I can manipulate numerators of a quotient. And I'll give you a simple example. If I had a quotient such as, let's say, x over x plus 2, the basic rule of thumb when dealing with a rational expression, a quotient of polynomials, is the degree of the numerator has to actually be smaller than the degree of the denominator. So I would need to do long division or synthetic division on this in order to get a simplified answer. Or I can simply add and subtract 2 to the numerator. And if I add and subtract 2, then I can basically pull apart the quotient as x plus 2 over x plus 2 minus 2 over x plus 2. And then again, paying attention, they have the same denominator, I'm just adding numerators, but this would then be 1 minus 2 over x plus 2. And the reason this is extremely valuable is if I had to integrate this original statement, I can't integrate that, but I could easily integrate this. So this is a common algebraic procedure I like to perform to make quotients just simpler to deal with. You can always do the longer synthetic division, but this will always be faster because adding and subtracting the appropriate term to the numerator means once I break it up, you can quite literally go from here to here without any in between. Now, this is going to come up a couple of times. So let's consider the next problem I want to do is the antiderivative of x times the inverse tangent of x. Now, I have a product of two functions. I know both of their derivatives, but I do not know the antiderivative of inverse tan. I only know its derivative. Therefore, based on what I said earlier, the inverse tan has to be my u. Okay? Then my dv will be x dx. Now with that, du will be the derivative of inverse tan, which is 1 over 1 plus x squared dx. And the v will be 1/2 x squared. So with this, once again, uv minus the integral of v du. Now I have that half, I'll just go ahead and put that in front. But then that gives me x squared over 1 plus x squared dx. And that's not really a form I recognize. I don't know any functions whose derivative looks like that. That looks fairly complicated. But if we did the long division here, because we notice the degree of the numerator and denominator are the same, or we can do the simple trick I just showed. See, if I've got x squared over 1 plus x squared, and I simply add and subtract 1 to my numerator, then I've got x squared plus 1 over 1 plus x squared, which is simply 1. Then I have minus 1 over 1 plus x squared. And again, a quick check, if you put these over a common denominator, you'll see I'll get back to the original. And so what that does is that gives me something I actually can integrate. So let me erase this. So this quantity right here would be nothing more than 1 minus 1 over 1 plus x squared. And of course, I know both of those antiderivatives. So that will just be x, and that's going to be inverse tan again. So inverse tan keeps showing up in this answer. So my final answer, I have an inverse tan here, I have an inverse tan here, and every term has a coefficient of 1/2. So once again, I can leave my answer in this form, but if I'm going to use this for further problems or a problem down the road, something bigger or something I have to evaluate, it may be a good idea to go ahead and try to write that in a more condensed fashion. So for one thing, I'll factor out the 1/2 from the entire thing. And now I have a plus inverse tan and an x squared inverse tan. So that would be x squared plus 1 inverse tan minus x. Again, this may be a simpler form to deal with because I only have the one fraction out in front. So this one was kind of a bear. And as always, whenever you're finding an antiderivative, the only real check is to differentiate it and see if you get back to the original statement. My suggestion, though, if you're going to do differentiation, do it in a non-factored form. It'll be a little bit simpler. Now, I want to do a similar problem to this one, just like the last one, but one maybe a little more complicated. Let's now take the same thing, but this time let's see, which one did I want to do? I want to do x squared times inverse tan of x. Now, clearly our choice of u and dv will mirror the last problem that we did, because again, we don't know the antiderivative of inverse tan, so that kind of has to be the u. And then the dv being x squared dx. And the derivative, once again, 1 over 1 plus x squared dx. And the v being 1/3 x cubed. So this is not a, not a very happy looking form, but I can at least write the next statement easily enough. So I'll have this integral is 1/3 x cubed times the inverse tan of x minus v du. So once again, I'll put the fraction in front and I'll have x cubed over 1 plus x squared dx. Now this one presents a little more of a problem. I can't add and subtract 1 to the numerator. That really won't help me. But what if, let me write it down here. What if I add and subtract x to the numerator? In other words, what if I do this? And the reason this is always legal is I'm essentially adding 0. You say, well, why would I want to do such a crazy thing as that? Because now my numerator would be x cubed plus x over 1 plus x squared minus x over 1 plus x squared. And this term right here, I can factor an x out. So I'll write like this. And you notice those will cancel. And this will simply be x minus x over 1 plus x squared. And once again, the check is if I put this over a common denominator, once again, I will see that I get exactly x cubed over 1 plus x squared. So this is what that particular quantity will reduce to this time. So this is then 1/3 x cubed inverse tan x minus 1/3 times the integral of x minus x over 1 plus x squared. And both of those are very, very friendly terms now. So here I'm going to get 1/3 x cubed inverse tan x minus 1/3 of 1/2 x squared. But you say, wait, I don't know what to do with the second one. Well, think u sub. If my u is 1 plus x squared, then my du would be 2x dx. So I can simply write a 2 and a 1/2. And then my antiderivative of that term will just be the natural log of 1 plus x squared. And I have that 1/2 now. Now, here's the thing. Generally, when we do an antiderivative involving natural log, we always say natural log of the absolute value of the quantity, and we put the absolute value just in case that argument can be negative. But the quantity 1 plus x squared is always positive for any real number x. So in this case, I can actually skip the absolute value. It's not incorrect, it's just not necessary in that case. So I have this beautiful final answer. Now, of course, I would want to distribute. I got to work with the negatives. And now, again, looking at my final answer, can I make that thing a little bit prettier? Well, if nothing else, every term has a fractional coefficient. Here's a 1/3, this would be a 1/6, this would be a 1/6. So in this case here, I would probably opt for factoring out the 1/6 and then just writing everything I have left. So I would write this as 1/6 times. I'm not a big fan of lots of fractional coefficients. I find it's a little bit messy. So then I would have something of this form. That's minus a sixth, and I factored out a sixth, so it'd just be minus x squared. This would be plus a sixth, so that's just plus log 1 plus x squared. And you see the final form is a little bit cleaner, less fractions. So here are some examples of more challenging versions of integration by parts, but the rule is still the same. If you have an integral of a product of two terms, even if one of the terms is a 1, you can always, absolutely always break it down into an integration by parts problem like we did here. The only question is, will you be able to integrate the new resulting integral? As long as you can, then integration by parts is usually the way to go.